I'm Eric Shidley, and this is Astronomy Fundamentalized, Lecture 7, Light. In this lecture, I'll describe electromagnetic radiation, commonly known as light, and identify its critical role in the science of observational astronomy. Light is an electromagnetic wave. Now, that certainly sounds very sophisticated to say, but one thing that's very familiar about it is the idea of waves. Whether we're talking about waves on a string or waves in the ocean, or the sound waves of my voice traveling through the air, all waves share some basic fundamental characteristics. The first of which is that they're described by a frequency and a wavelength. Here, in this equation, the frequency, f, is multiplied by the wavelength, represented by the Greek letter lambda. The frequency is measured in hertz, or cycles per second of the wave. That's how many times per second the wave does its waving thing. And the wavelength is the distance from peak to peak, from one wave crest to another. And again, it doesn't matter if I'm talking about ocean waves or waves on a string or waves in the air. Any kind of waves have a frequency and a wavelength. And when you multiply them together, you get the wave speed. Now, in the case of electromagnetic waves, what's waving is not as easy to see as when I look at ocean waves. When I look at the ocean and see waves, I see the water going up and down. When I look at waves on a string, if I take one end of the string and I shake it back and forth and produce waves, I see the string moving up and down. It's less obvious, but still a bit tangible, that when waves travel through the air compresses and stretches. Well, when electromagnetic waves travel through space, it is electric and magnetic fields that are doing the vibrating. It's the electric and magnetic fields that increase and decrease through space. This is not a detail, certainly very interesting science, but it's not an absolutely critical detail for our understanding of how light relates to astronomy. But it is important to recognize that there is a frequency and a wavelength, and when you multiply them together, you get the speed. In the case of light, it's very commonly known that the speed of light is an interesting number indeed. If I'm talking about vacuum space, a region in space where there's absolutely no matter whatsoever, then the speed of light is 3 times 10 to the 8th meters per second. Spectacularly large number, and indeed, so far as we can tell, the ultimate speed in the universe. There's nothing that can travel even that fast. It is the ultimate speed. And it's the way, on an aside, how we define our light year. A light year is the distance that light travels in 1 year at this fantastically large speed. This is the reason, obviously, why a light year is such a great distance. So light is an electromagnetic wave. And the other property that's really important, that it shares in common with other waves, is that it carries with it energy. A source of light throws out energy in all directions. In this way, we say that it's radiant, or that light is a form of radiation, because it delivers energy in principle in all directions. And so we can say electromagnetic radiation, we can say electromagnetic waves, but basically when we say all of those things, what we're talking about is light. So light is the simple word that we use for the more sophisticated concept of electromagnetic radiation. When I say light, it might cause you to think about visible light, the light that I can see, the colors of the rainbow, for example. Well, here on this spectrum, we see that when I look at all of the possible wavelengths of light, represented by the red arrow just below the rainbow there, that the range of wavelengths is large indeed, from, on this diagram, 10 to the 4th there on the left. Very, very long wavelengths. This is measured in meters, so it's 10 to the 4th meters. That's 10,000 meters. And on the right is 10 to the minus 16th, a very, very small number of meters. So when I characterize electromagnetic waves, when I characterize light by its wavelength, there's indeed a wide range of wavelengths, and the light that I can see, visible light, is only a very, very narrow band in the middle, from wavelengths about 700 nanometers to 400 nanometers. There are other forms of light that I cannot see, but their names are very familiar. Starting on the right with very, very long wavelengths are radio waves. Next come infrared, with wavelengths just longer than the sensitivity of the human eye makes visible. Then I have the narrow band of visible light, and beyond visible light, ultraviolet. Ultraviolet makes sense because 400 nanometer light on the spectrum is turning purple. It's becoming violet. And it goes just out of visible range. It becomes the ultraviolet band of the spectrum. And then I have next X-rays in the vicinity of 10 to the minus 12th meters. And then gamma rays, the shortest wavelengths of all. Now, an important idea to keep in mind, absolutely critical, even if you're not going to do a technical study of astronomy, is to recognize that the wavelength of light is indicative of the energy in the light. So when I look at light of very, very long wavelength, I should think low energy. Long wavelength is low energy is red. Notice that the red end of the spectrum has a longer wavelength than the blue end of the spectrum. So in my mind, I should always have long wavelength, low energy, red. Long wavelength, low energy, red. The opposite side, short wavelength, high energy, blue. This is something that we should definitely commit to memory because it's an idea that's pervasive in astronomy for simple reasons. If I say that I look through my telescope and I see a blue star and a red star, I know that the blue is a short wavelength and therefore a high energy. I might therefore conclude that the star is of a high temperature. The red star that I see through my telescope is at a longer wavelength, is a lower energy, and therefore a lower temperature. So developing a habit of mind where this becomes automatic is an excellent, excellent idea for the beginning astronomer. Here's the spectrum again, but with a better sense of scale. Right in the middle of the diagram, I see the wavelength of the light, all stretched out where the distance from peak to peak is quite large on the left-hand side, and on the right-hand side, the peaks of the wave get very, very close together. That's a short wavelength. Similarly, this spectrum, just like the one on the last slide, is arranged from long wavelength, low energy red to short wavelength, high energy blue on the right-hand side. But we're given some sense of scale here where the radio waves are on the scale of Mount Everest and the gamma rays are on the scale of the atomic nucleus. Again, the ultraviolet, X-rays, and gamma rays are the high energy region of the spectrum, where the radio and infrared are the low energy range. If you think about your everyday life, this makes sense, because right now, as you listen to this lecture, you are immersed in radio waves and infrared radiation given off by every hot object in your vicinity. These radiated emanations, whatever you want to call them, are very, very low energy, which is good, because if they were high energy, they would interfere with your biology and be dangerous. Our environment would be uninhabitable. Ultraviolet, X-rays, and gamma rays are the dangerous ones. Note that you put on sunscreen to avoid absorbing too much ultraviolet radiation. You're also told not to get too many X-rays in the course of a year, because X-rays are dangerous, and indeed, gamma rays are lethal to humans in appropriate doses. So it's the ultraviolet, X-rays, and gamma rays that carry the most energy. That's what makes them the most dangerous. Now, as electromagnetic radiation, as light travels through the universe, it interacts with matter. If it weren't for matter in the universe, the light would just travel on in a straight line forever and ever and never stop, and the universe would be far less interesting. But when light encounters matter, an interaction takes place that changes the matter in a variety of ways, but more importantly, changes the character of the light. It turns out to be an essential idea of astronomy that light is modified when it interacts with matter. So this interaction takes place in several ways: reflection, refraction, diffraction, absorption, emission, and believe it or not, gravitation. I can go out to the hardware store and buy a laser level. It's a little contraption that I put on some sort of a tripod or something, and it shoots lasers out in all directions. And I'm told that each one of those laser points that it creates will be at the same height, and therefore I can I make measurements and do construction and level. Because unlike a bullet fired from a gun, which curves downward towards the surface of the Earth and the influence of gravity, a laser beam is absolutely straight, right? Well, the truth of the matter is no, it's not absolutely straight. And in fact, the laser, as it travels horizontally over the surface of the Earth, curves toward the Earth under the influence of the Earth's gravity. But just like a bullet that's fired so rapidly from the barrel of a gun, it doesn't curve much. If I throw a baseball, for example, it's obvious to everyone that it curves to the Earth. If I fire a bullet, it travels very much in a straight line, but if I want to hit a target far away, I have to aim upward in order to account for the arc of the bullet as it travels. And a laser beam travels at such a high rate of speed that the curvature of the beam is extraordinarily slight. In fact, it's so slight that I can use a laser leveling device. But nevertheless, light and gravity have a kind of interaction that we'll be interested to talk about later in the course. Reflection is an important interaction in astronomy because just like light reflects off a mirror or light reflects off objects in your room so that you can see them. For example, I have a coffee cup on my desk that contains a bunch of pens. The way that I see it is that light from the window reflects off of that surface and comes to my eye. If the matter did not reflect the light, then no light would come to my eye and I would not see the object. That's a difficult thing to get your head around as you look around the room and realize that if it were not for reflection, you would see absolutely nothing. Our sight and our interaction in our daily lives depends heavily on this. As I look up into the sky, I would imagine that every star in the sky is a point of light that emits, like a light bulb, electromagnetic radiation that comes to my telescope and therefore comes to my eye. However, there are things in the sky which reflect light. This reflection nebula is an example. Starlight is literally reflected off the nebula, making it visible. If this nebula did not reflect light, then I would not see it. Refraction is another interaction between light and matter, and it takes place because the speed of light is different in different substances. I mentioned previously that the speed of light in vacuum is 3 times 10 to the 8th meters per second. But when light travels through any matter at all, whether it be solid, liquid, or gas, its speed is reduced. In fact, the speed of light in any given substance is of issue, and you can look up the speed of light in this kind of glass or the speed of light in water and air and hydrogen, carbon dioxide. Whatever type of substance you're interested in, the speed of light is different. When light changes speed going from one substance to another, it causes the direction of travel of the light to bend. This process is known as refraction. Obviously, the way in which this is important to astronomers is that telescopes, which use lenses to focus light to be viewed, rely on the phenomena of refraction to focus light to the human eye to be viewed. Diffraction is a process whereby light bends around obstacles. It's a little bit hard to understand how light could bend around the edge of an object, but it's easier to understand how sound waves, which are like light waves in most respects, bend around corners. Imagine that you're sitting in a classroom and there's something going on in the hallway, some sort of ruckus. And despite the fact that you cannot look out the door and see what's going on, you can still hear it. The reason for this is that the sound waves that are produced outside in the hallway bend around the doorway and can come into the door to go into your ear and stimulate your tympanic membrane, and you get the sensation of the sound. If it weren't for diffraction, the sound waves would never come into the room, and you would be unable to hear things that you did not have direct line of sight to. The same thing is true for light, although, because light travels at a much greater speed and has much shorter wavelengths than sound does, that the diffraction effect is quite small indeed. But remember, when doing astronomy, we're looking at very, very small angles. I'll ask you to recall the light second, or I'm sorry, not the light second, the arc second. That is 1/60th of 1/60th of a degree, 1/3600th of a degree. That's a very small angle indeed, and those sorts of angles are the angles through which light bends when it encounters an obstacle. This image here is light bending around a circular obstacle. One of the chief ways that absorption and emission, or that light interacts with matter, is absorption and emission. And so I'm going to be asking you, the listener, to cast your memory back to your studies of chemistry, when you learned that in atoms, electrons arrange themselves in energy levels. Perhaps some of you remember electron dot diagrams, figuring out how many electrons were in which level. It turns out that atoms can absorb and emit electromagnetic radiation according to these energy levels. What happens is an electron sitting in a low level absorbs a quantum of light and then jumps up to a higher energy level. We call this process absorption, where the electromagnetic radiation, where the light is absorbed by the electron, and therefore the electron gains energy. Later on, that electron will lose that energy and drop down to a lower energy level. The law of conservation of energy demands that this dropping down of the energy level requires the emission of electromagnetic radiation to carry the energy away. So atoms can both absorb or emit electromagnetic radiation, but there's a catch. The electrons arrange themselves in atoms so specifically that they can only accept certain amounts of energy. That is, that from one energy level to another is a very, very specific distance, and they can only absorb that energy. Since the energy of light is associated with its wavelength, that means that an electron looking to jump up a level can only absorb light of a very specific wavelength. Similarly, an electron that's looking to drop down a level can only emit light of a very specific wavelength. So the basic idea here is that when atoms interact with electromagnetic radiation, the absorption and emission of light is associated or keyed to the wavelength. So what I have here is a little diagram of electrons dropping down from these various levels, and the levels are associated with wavelengths. This is just a basic diagram of how we visualize electrons transitioning from one energy level to another. Notice that there are many different levels that electrons can travel between, and in fact, all of these are shown going downward, losing energy and therefore emitting electromagnetic radiation. The fact of the matter is that all of these can be reversed and can become absorption. And so below, we see what is called the emission spectrum and the absorption spectrum for this particular atomic configuration. Now, what we see here is that light is emitted by the atom, and it's put through essentially like a prism to separate it into its individual wavelengths. What we're looking at here is essentially a rainbow. But you'll notice that in the middle strip there, it's mostly black. Most of the rainbow is missing. Only very specific wavelengths are present. And that makes sense, because when the electrons drop down in the energy levels of the atom, they can only emit very specific wavelengths. The other ones aren't there because they're not possible. And so therefore I get this little pattern where there are a couple of purples and a blue and an orange at 656 nanometers all the way over on the right. Now, if I were to shine light on this atomic system, then those electrons which drop down to lower levels would jump up again by absorbing light of the exact same wavelength. So if I pass light through the atoms and look at the light on the other side, I get the rainbow spectrum, but with some very specific wavelengths missing. Those wavelengths are the wavelengths that were absorbed by the atoms. So I have a spectrum of light that was created by the emission from the atoms, and I have a spectrum of light that was created by the absorption of light by the atoms. The former is called the emission spectrum, and the latter is called the absorption spectrum. Here are some spectra for some atoms, and I have this slide here for one very specific purpose. Look at helium, sodium, and neon. They are absolutely distinguishable from each other. The difference between them is dramatic. It is not in any way subtle. Because helium, sodium, and neon have different numbers of protons, neutrons, and electrons, the atomic behavior of the electrons in terms of how their energy levels are arranged is completely different. And so each spectrum, here emission spectra being shown, each emission spectrum is a fingerprint of that type of atom. And this turns out to be an extremely important notion for use in astronomy. It goes something like this. Here I have, in the middle of the diagram, a source of light, a light bulb. For our purposes, the light bulb is standing in for a star, which would emit light because it's a hot object. Now, the light from the light bulb travels to the left, to a prism which separates the light into the rainbow spectrum that we're familiar with. I'll warn you that the spectrum is here, well, not reversed, but it's the same way it was in the previous one. But from time to time, the spectrum gets reversed back and forth because it doesn't matter in which way you view it. Here I have the blue wavelengths on the left. The blue wavelengths are the short wavelengths, high energy, and the long wavelengths on the right. The long wavelengths are long wavelength, low energy. But at any rate, I get the continuous spectrum. The hot light source produces all wavelengths of light. It doesn't produce them with equal intensity. As you see, the spectrum intensity curve there above has a little bit of a curve to it, but nonetheless, there are no holes in the spectrum, and there are no especially bright parts. If I look at the hot light source again, and the light that travels to the right and is allowed to travel through a cloud of gas, two things happen in this thin cloud of gas. One is that the light travels directly through the cloud of gas and arrives at a prism where, once again, we resolve it into its spectrum, but we discover that as the light traveled through the cloud of gas, there were wavelengths that were absorbed by the atoms in the cloud. And those wavelengths are represented by the holes in the absorption spectrum. And we see in the intensity that there are downward spikes, which represent the missing energy, the energy that was absorbed by the atoms. Now, these atoms in the gas will ultimately re-emit this electromagnetic radiation in random directions. So the emitted intensity is reduced by the fact that it goes off in all directions, but I'll take a slice of that intensity, which goes down and to the right, the slightly red-colored beam, and put it through a prism and separate it into its wavelengths and discover that I get some of the original radiation just by scattering, but I get these very, very specific wavelengths. Notice that if I took the emission spectrum shown in the bottom box and slid it directly into the absorption spectrum, that it would fit like a puzzle piece, giving me the entire spectrum give me the entire spectrum. Sorry, I had a little hiccup in the lecture notes there. Here we see a graph of the electromagnetic radiation that's emitted by a hot object. It turns out that every object in the universe that has a temperature above absolute zero emits electromagnetic radiation. You, as you sit listening to this lecture, are emitting light. Now, this is not light that you can see because the light emitted by human beings is infrared. Notice on the diagram, a human with a body temperature of 310 Kelvin emits a very, very long wavelength of light, measured in nanometers here, and it's in the infrared band of things. So this is why, if one puts on a pair of infrared goggles, you can see people in the dark of night by the electromagnetic radiation that they emit. The other three bands are radiation emitted by stars, and we see that there's some interesting features to these three graphs. The star that has a surface temperature of 3000 Kelvin produces a much lower intensity. Its temperature is lower, and so it's not as bright, which is a notion that I think that many of us might have guessed. Notice also, though, that the peak intensity that it emits is in the infrared range. The next star up, our Sun, with a surface temperature of 5,800 Kelvin, is brighter. That is, it generally produces a larger intensity. And it has a peak intensity wavelength that's sort of green-yellow in the spectrum there. This is why our Sun appears yellow, because its peak emission is in the range of the visible spectrum. This is not surprising. Human beings evolved on this planet, so it makes sense that our eyes would have adapted to be most sensitive to the wavelength of greatest intensity emitted by our own Sun. A star with a higher temperature, say 15,000 Kelvin surface temperature, produces a maximum wavelength of in the blue range, in the ultraviolet range. And so what we see here is two things demonstrated by this graph. One is that the hotter an object is, the brighter it is. That is, its intensity is greater. And also, the hotter an object is, the bluer it is. This verifies our former suspicion that a blue star producing long wavelengths and therefore light of very high energy would be a higher temperature star. The higher temperature corresponding to the higher energy. This is the general idea. Imagine that you take an iron poker and you put it in a fire. As it heats up, two things happen. One, its brightness increases. As it begins to glow, the hotter it gets, the brighter and brighter it glows. There's a physical law associated with this. It's called the Stefan-Boltzmann law. It says that the hotter an object gets, the brighter it is. And in fact, it says that if the temperature is measured in Kelvin, the intensity emitted is proportional to the temperature to the fourth power. That means that if an object gets twice as hot, then it's 16 times brighter. So indeed, the hotter an object is, the brighter it is, according to that Stefan-Boltzmann law. It's also true that the hotter an object gets, the bluer it gets. In fact, an object starts out glowing red, and then glowing orange, and then yellow, and then white. The white glow is actually, because it's gone very, very high intensity blue. This is associated with a physical law known as Weans Law, and it's possible to calculate that, in fact, the wavelength of light is inversely proportional to the temperature. So by looking at the wavelength of light from stars, for example, it's possible to know both the intensity and the temperature of objects just by observing the wavelength. So what we can do now is take all of these ideas and put it together in the form of a kind of mystery. Here we have a spectrum that was taken in by a telescope and put through a prism, and then we see that there are some absorption lines right around where it says wavelength. There are some lines missing from the red, and then further along to the right there are some lines missing as well. And there are also some emission lines that on the left-hand side, there are some bright violet lines that we can see. Also, we notice that the intensity varies in some strange ways. It's not a uniform intensity, but there's a peak around the greenish-red sort of area of the spectrum, and there's also a peak in the infrared range of the spectrum. So how do we interpret this, and what can it tell us about the object that emitted this light? Well, there are a couple of conclusions that we can draw. First of all, there is a peak that is in line with the thermal emission from the sun. Here, the thermal emission of the sun is shown as a dotted line, and directly beneath it is the peak on our spectrum. So the idea here is that the object reflects sunlight, but it doesn't reflect the blue portion of the sunlight, only the red portion of the sunlight, and so the surface of the object appears red. The absorption spectrum is compared to known absorption spectra. It's like a fingerprint. All you have to do is go in the library, or in the laboratory, pardon me, and do experiments with various substances and find out what their spectra are, and then you can look at some unknown spectra and immediately identify that the absorption bands in the spectrum are associated with CO2, carbon dioxide absorption. On the left-hand side of the spectrum, the emission lines are associated with ultraviolet emissions of atoms at very, very high temperatures. And on the right-hand side, The thermal peak indicates a surface temperature of the object about 225 Kelvin. So all of this information together, and perhaps you've figured it out by now, this is actually a spectrum from the surface of Mars. Notice what we've learned just by observing the light that is reflected from Mars. We learn about its upper atmosphere, we learn about its lower atmosphere and that there's largely CO2, and we also figure out the average surface temperature by the thermal emission peak on the right-hand side of the spectrum. And so there's a fantastic amount of information which can be gleaned by looking at the spectra. Spectra is one of the chief tools available to astronomers to draw conclusions about the chemical nature, temperature, and intensity of objects which are too far away to measure directly, which just about everything in astronomy is. There's another property of electromagnetic radiation that's frightfully useful to astronomers, and it's called the redshift, otherwise known as the Doppler effect. You may have noticed that, for example, a race car, when it's approaching, the engine sounds like it has a very high pitch, a high frequency to it as it approaches the listener. And as it passes, it goes to a very, very low frequency. Basically, it sounds like and the frequency goes down as the car passes. This is not because the driver of the car has shifted or something has changed about the way the engine is performing, but the fact is that the engine of the car produces sound waves, and as the car approaches, those sound waves are compressed so that the wavelength is shorter, so that the pitch of the sound is higher. And as the race car passes and travels away from you, it's traveling in such a way that it's it's running away from its own sound waves. And so the wavelengths of the sound are larger and therefore lower in pitch. The same thing is true for electromagnetic radiation because it, like sound, is a wave. Here in the top of the diagram we have a light source that's producing light of a particular wavelength. The waves travel away, and then we have an observer in the space shuttle here. It's important to point out that the space shuttle in this situation, I want to say, is not moving relative to the source. And so the observer on the right and the observer on the left measure the same wavelength because the light comes to them in identically symmetric way, whether it goes to the right or to the left. In the bottom diagram, however, the light source itself is moving relative to the observer. So as it moves and emits wavelengths, as it travels to the right, it's chasing its own wave. And as it travels away from the left, it's running away. And so we see by this diagram that the wavelengths to the right are compressed. They are shorter wavelengths, and the shorter wavelength is the higher energy, is blue. And to the left, the wavelength is longer. Longer wavelength, less energy, red. So as a source of light moves towards you, it will appear bluer. And as a source moves away, it will appear redder. We call this phenomenon redshift because it turns out that many of the objects that we view in the night sky are redshifted, but more about that in a moment. An immediate question arises that if I look at a star and I say, wow, that star appears blue, how do I know that that star is in fact coming toward me? Because a star that appears blue, as I look at it through my telescope, could have been blue in the first place. How do I know that it has been shifted to the blue? Well, once again, I go back to my spectra. Here, if I look at the spectra emitted by a star, I see some absorption lines. This is because the light emitted by the star, some of the light emitted by the star, is absorbed by the gases that shroud the star. And so I get this absorption spectra, and I can look at in my laboratory results and compare it to elements that I know of here on Earth and say, yes, I recognize this oxygen, and this is nitrogen, argon, titanium, whatever they happen to be, and I identify those, and there they are. This is the way they look when they are unshifted. If I'm looking at a red-shifted spectra, I see the same pattern of lines. That is, I see the same thumbprint, but every single line is shifted to the right in this diagram by an equal amount. The spacing between the lines hasn't changed, and so I can still identify it as the pattern associated with specific atoms, but the entire thing has shifted to the right. The entire absorption spectrum is red shifted. The same spectrum again in the last spectrum here on the list is shown with the same absorption lines again, but all equally shifted to the right, blue shifted. In this way, I can look at individual stars and determine whether that star is coming toward me or away from me based on the red shift or the blue shift. Now, here comes the interesting point. Once you're armed with this knowledge, you get yourself a telescope and you look deeply into space, and you start looking at all of the stars around you to see which ones are coming toward us and which ones are going away from us, so that you get an idea of the relative motion of our universe. And when you look nearby at local stars, some of them are coming toward us, and some of us are going away. But when you look out in the universe and look at galaxies, you look at this galaxy and you do some measurements and you say, oh, look, it's redshifted. It must be traveling away. And another one over here and it's redshifted. Another one over here and it's redshifted and redshifted and redshifted. All of a sudden, we look out at our universe and find that just about everything that we look at is redshifted. Everything in the universe is traveling away from us. That's why this particular phenomenon is not referred to as shift, but redshift. Because, yes, there are objects that are blue shifted because they're approaching us. But by far, everything in the universe is traveling away. Now, if you think about that, ponder it. It's a very, very mysterious observational result. Everything in the universe is traveling away from us. This might lead you to the conclusion that, well, we're at the center of the universe and the universe is expanding, so everything's going away, right? Well, the fact of the matter is that there's no evidence that we are at the center of the universe, and this mystery has driven cosmology and fascinated the human mind for decades, and will continue to do so in the future. Everything around us in the universe is traveling away. Where's it all going?